Hello everyone, and welcome to my second tutorial video covering example problems from section 1.6 in the textbook. This tutorial video will be covering homogeneous equations, and this is a more specific example or case of differential equations that can be solved using the substitution method. For more details and instructions on how to use the substitution method in general, please see my tutorial video on that topic, which I should already have posted on YouTube. I will also post the link to that in the description. Alright, with that said, I'm not going to go over all of those details again in this video. I'm going to mostly just address everything that is more specific to homogeneous equations. Okay. Now, before I write out exactly the example problem I want to tackle, I want to sort of quickly recall what homogeneous equations are. And I have written these at the top. Homogeneous differential equations are ones that have the form dy dx on the left-hand side is equal to some right-hand side, which can be expressed as a function of y over x. So if you can manipulate a differential equation that you're given and do so in such a way as to be able to write the right-hand side of that differential equation as a function of just y over x, then you are working with a homogeneous equation, and there is a very simple, very standard substitution that you can use to solve the problem. All right. So what do we do in these cases? Well, it turns out that we always use the same substitutions. So once you have identified that you are dealing with a homogeneous equation, you can always use the following substitutions. Now, as with the more general substitution methods that I went over in that other video, I do expect you to write all three of these substitutions out on your on the paper that you turn in to me if a problem like this ends up on an exam. So the primary substitution that we are always going to use is going to be to set our v to be equal to y over x. And if we proceed exactly as I instructed you, again in the substitution method video, you'll see that I also ask you to then write out, if you're using this as your v, write out what must be y equal to, and you'll see that therefore y, in this case, is going to always be equal to v times x. And the third thing that I ask you to always write out is write out, therefore, what must dy dx be equal to. And if you see this, in this case, if y is equal to v times x, then you'll see that by product rule, dy dx will always be equal to v plus x dv dx. Now, these three substitutions, really, they all just come from the simple choice of v equals y over x, are the substitutions that you will use every single time that you encounter a homogeneous equation. They should always work out for you. They should always turn the problem into something that you can resolve sort of simply and hopefully in a relatively straightforward fashion. The bigger difficulty with homogeneous equation problems is often in that very first part, the fact that you need to identify that the equation that you're dealing with is a homogeneous one to begin with. So with that said, I'm going to jump directly into an example. I'm going to leave this up on the board as we work through this problem, just so you can refer to this. This is our main idea, but let's talk about an example and show how we can manipulate, fiddle with an equation, and reach a point where we realize that we are working with a homogeneous equation. Alright, so for this example problem, I will be using exercise 1.6.9, which is a nice example of a homogeneous equation problem, which doesn't necessarily immediately look like a homogeneous equation right on the get-go. So 1.6.9 just, of course, means that it is homework problem number 9 listed in the textbook from section 1.6. A variation of this is, I believe, on your third homework set that I have assigned. And this exercise is just asking you to solve the following differential equation. We have x squared times y prime is equal to xy plus y squared. Okay, so this is going to be the problem that we are tackling. And the very first thing that we're going to have to deal with is be able to recognize, get to the point where we even can recognize that we are in fact dealing with a homogeneous equation. So I'm going to write this as step 1. Let's just consider this for now as a differential equation that we can tell certainly does not appear to be immediately separable, is definitely not first order linear, but we're not entirely certain yet how we're going to tackle this. So to get to that point, the very first step is basically to fiddle with it algebraically. So do some algebra. Try to put everything except the y prime, the y prime on the right-hand side. Look for patterns. This can often involve tricks like factoring or, multiplying things out. All sorts of different things can be used here. We'll see how this goes in this example. So in this case, the very first thing that we're going to do, like I said, we're going to try to isolate everything except for the y prime on the right-hand side. And that means that we're going to have to divide on both sides by x squared. So if we divide on both sides by x squared, we get the following. We're going to get that y prime is going to be equal to xy plus y squared divided by x squared. Okay, now where do we go from here? Well, first off, recall that although you absolutely are not allowed to split addition in the denominator of fractions, you are allowed to split addition in the numerator. So in this case, because we have an addition in the numerator, we're allowed to split this up as follows. This is going to be equal to xy over x squared plus y squared over x squared. And you can see here that we're going to have a little bit of cancellation. So specifically, this x up here and this squared down here will cancel each other out. All right, why is this useful? Why have I done this? Well, we can see that this gives us, I'll just get lazy and write get again. We get that y prime is going to be equal to y over x plus y squared over x squared. All right, now how are we any further along at this point than we were before? And at this point, I think I'm going to give you guys a couple of seconds to look at this and see if you can figure out what the pattern is that you should be able to spot here. What is it that makes this a good example that I have selected of a homogeneous equation? Feel free to pause the video if you want to test this out for yourself. All right. Well, the thing that you need to spot here to recognize that this is a homogeneous equation is that we have an addition of two terms that can both be expressed as functions, in some sense, of y over x. So first off, we have very clearly just y over x all on its own over here. But y squared over x squared can also be rewritten as a function of y over x. So if I rewrite this as follows, you'll see that this is y over x plus, in parentheses, y over x, that whole thing squared. And now we see that this entire right-hand side of this differential equation is just basically a function of y over x. So this guy here is homogeneous because we have y over x, and no other variables show up anywhere outside of this. This guy is homogeneous. Great. Now that we've identified that, the process for actually solving homogeneous equations, as I've mentioned, is very straightforward. You're always going to use the same substitution. You don't have to look around, try to spot, try to think, or try out. There's no trial and error involved or anything of the sort. You just plug and chug, and you should get to a point where you get a differential equation that you can solve. All right, I'm going to move this step over here, and we'll move on to step 2. Now I've already written out what step 2 is always going to be up in the top right-hand corner of this whiteboard. So step 2 is to use the following. Oh, and by the way, on an exam, I do expect you to point out at the end of what I've written here in step 1, do write out explicitly on your paper that you have noticed that you are working with a homogeneous equation. That shows me that you are spotting the right thing and that you are using the correct method. All right. Once you've done that, step 2 is very simple. You just say that you're going to use the following substitutions. And you can just write this out verbatim on whenever you complete a problem like this on the exam and be perfectly fine. And those substitutions are exactly the ones I have written in the top right. We are using v is equal to y over x. Y is going to be equal to v times x. And we're going to be having dy dx be v plus x dv dx. Okay, now that we've written that down, let's actually write out what we get when we perform this substitution. We get the following. And as usual, I will try to color code the substitution to make it very clear to everybody exactly what I'm doing here. We have y prime is equal to y over x plus, in parentheses, y over x squared. So very clearly, the y prime is going to be, which is dy dx, is going to be replaced by, on the left-hand side, v plus x dv dx. And on the right-hand side, our y over x will be replaced with v, and our y over x squared will be replaced with v squared. And you can see that what I have done is in the original equation I replaced the y over x squared with v squared and the y over x with v. And then I replaced the y prime, which is dy dx, with v plus x dv dx. Now in this case we did not have to use that middle second substitution because there were no just singular y's lying around. And that's not a problem, that just means that things were a bit simpler than they might occasionally be. Okay, now that we have performed the substitution, we need to move everything around and be able to express this new differential equation as a type of differential equation that we know how to solve. In other words, we need to make this look like something that is either separable or first-order linear. So let's get this out of the way and move on to that next step. All right, now believe it or not, it turns out that whenever you do this type of substitution with a homogeneous equation, the resulting new differential equation you end up with should always be specifically a separable one, which means that you don't even have to worry about the whole first order linear thing. But if you are working with a homogeneous equation and you've done your substitutions correctly, it should always be separable, and you just need to make it look like that. So now you just need to, in step 3, write this new equation as a separable one. That means that we're just going to move everything except the dv dx over to the right-hand side and show that it has the proper format. So in this case, you'll see, I'm going to use just pencil here. If we look back above at the differential equation that we got, you'll see that we have this v here and this v here, and that those are going to cancel out because they're on either side of the equal sign. But we're still going to have that x in front of the dv dx, and we're going to need to divide on both sides by that. So what do we get? Well, you'll see that we get that dv dx is equal to v squared over x. And you can see that this is separable, because this is a function only of x being multiplied by a function only of v. In this case, the function only of x would be 1 over x, and the function only of v would be v squared. Now, once we've done this, the next step is to separate the variables. So this just means move all of the v's over to the left-hand side and all of the x's and dx's over to the right-hand side. And doing this, we get that we have 1 over v squared times dv is equal to 1 over x times dx. Okay, we've done all the manipulation that we need to do, so now we are ready to get to solving. At this point, we're just working with a standard separable differential equation. We've already separated the variables. There's nothing new or fancy in anything that I'm going to do in the next couple of steps. Step 4 is, of course, just integrate. And by integrate, I do, of course, mean integrate on both sides. So we are going to get integral of 1 over v squared dv is equal to the integral of 1 over x dx. Now you'll notice that whereas the right-hand side is going to give us natural log, the left-hand side will not. The left-hand side is just a power rule. So by the power rule, we get the following. We are going to have, if you write this, let's see. If you write this guy as being equal to v to the negative second power, the power rule states that the integral of v to a power, in this case negative 2, is going to be 1 over the new power, in other words 1 over negative 1, times v to the new power, which is 1 higher than the previous one. So we're going to have 1 over negative 1 times v to the negative first power. On the right-hand side, we just have natural log of the absolute value of x plus c, very standard integral to perform. Now, of course, that 1 over negative 1 is just going to be a negative sign in front of our v to the negative first power. I don't really like it being there, so I'm just going to pass it over to the other side. So here I'm just going to write thus. We get that v to the negative first power is equal to negative natural log of x. And we can keep a plus in front of the c, because minus a constant and plus a constant are the same thing. Okay, we are done with the integrating. In fact, we have, for all intents and purposes, solved that new differential equation. So as usual, there is only one step left to perform, which is the final one, step 5. substitute back. So substitute the original variables back. So now we see that we have v to the negative first power, and we'd used originally that v was going to be equal to y over x. So this v here, which I'm going to box in red, is going to be replaced by that very same v equals y over x that I have boxed in red further up. Doing this gives us that y over x to the negative first power is going to be equal to the negative natural log of the absolute value of x plus c. And again, this was very straightforward. The only thing that had to be substituted here was that v. All right, let's see if maybe we can get this, hopefully, in an explicit form. Now, y over x to the negative first power just means you take 1 divided by whatever was raised to the power. 1 over a fraction is just that fraction flipped. So in other words, what we get here is now x over y is equal to negative natural log of the absolute value of x plus c. Okay, so at this point I'd like to make a quick note about answer formatting, especially in the context of an exam. So on the homework sets, on the homework system, usually speaking, they will tell you the format that they expect of you. So specifically, if they want an explicit solution, which means a y equals something blank, that you have to input on the right-hand side, they will usually make that clear to you. And if they want or accept an implicit solution, the kind of solution that I will have discussed in the previous video on the substitution method, they will also have made that clear to you. Now, if on the exam I do not tell you very clearly that I want the solution in one format or another, then I will generally accept the solution in any format. So if I were on the exam to have given this problem and not told you exactly how I expect you to format your answer, I would consider this at this point to be a reasonably a reasonable correct answer at the end of the day. This is an implicit solution. But in some cases, I will ask you guys to write your solution in an explicit format if possible. And if I ask you to do so, then I expect you to at least make an attempt to see if you can get an explicit solution y equals something, and at least make an attempt there. And so if I were to have asked that of you, I would be basically requiring of you that you see if you can go a little further and isolate y all alone on the right-hand side. So we're going to go ahead and do that now. So there's nothing too fancy going on here. All I'm going to do is divide on both sides by x, and then I'm going to flip these fractions. So at this point, to get an explicit solution, so first divide on both sides by x, and doing so will give us 1 over y is equal to negative natural log of x plus c divided by x. And then, very simply, flip both fractions. And doing so will give us our final explicit solution, y equals x divided by negative natural log of the absolute value of x plus c. So once again, this is the way I'd expect you to format your solution on the exam if I were to have explicitly stated in the question that I wanted you to present your answer in an explicit format if possible. If I didn't explicitly state that, then starting about, shall we say, here, either of these two, these are fine implicit solutions. But this is the only explicit one. All right. Hopefully that makes it clear what I expect you guys to show when you're working on a problem like this on the exam. Again, like I said, most of the difficulty in homogeneous equation problems is usually in even figuring out initially that what you're working with is homogeneous at all. Once you realize that, once you've figured that part out, everything else is pretty straightforward, is all very much by the book. You always use the same substitutions. You'll always get specifically a separable differential equation. We've already gone over the specific set of steps that you need to go through to solve a separable differential equation. So after that point, everything is hopefully pretty straightforward and not too difficult. All right, so I think that's all of the tutorial problems I'm going to go over on from section 1.6, at least for now. If there's any other additional problems from this section that you guys would like me to make a tutorial video ahead of the exam, please let me know. I'm very happy to do this. And otherwise, that basically sums up for this section. I'll have a couple more tutorial videos coming later on covering some problems from the earlier sections, which I didn't address yet in a video like this. But yeah, regardless, as usual, let me know if you have any questions or if there's any other topics you'd like me to cover. And until then, I hope you guys stay safe and stay healthy. And good luck with the upcoming exam.